Hello, and greetings from the Russian Orthodox Church behind me here in Vienna. And it is cold in Vienna, and there's nothing I like doing more when it's cold than talk about chemical bonding. So yeah, this is chemical bonding part 2, how to bond. So let's see how we do. All right, so there's different energy levels. The atoms in the first level always want 2 electrons. Each level after that wants 8 electrons, so it goes 2, 8, 8. This is also known as the octet rule. And just so you know, these apply to elements only 1 through 18 in the periodic table. All right, so atoms must combine in a certain way to become stable so that they'll bond. Stable means that all the outer electron layers are filled, has all the electrons that it needs. So if the outer level does not have enough electrons, it must either steal or share those electrons. So basically it connects to other atoms in order to get the electrons that it needs. This is what bonding is. All right, so how to bond? Let's figure it out. First, bonding between molecules is all about stealing and sharing electrons. So you need to figure out how many electrons are available for stealing, sharing, bonding. Each atom wants an inner level of 2 electrons, again with the octet rule, a pair. So it wants an outer level of 8 electrons, again octet rule. The valence electrons are in the outermost energy level, and these are the electrons that are available for bonding. All right, so types of chemical bonds. You've got an ionic, a covalent, and polar covalent bond. So let's talk about an ionic bond. An ionic bond is a bond between 2 oppositely charged atoms. So it's formed by electron stealing and possibly dropping as well. So you want to bond because opposites attract, which is the opposite's the overall charge of the atom. So think about it as magnets. You know how you have a positive and a negative? The magnets come together. That is very similar to ionic bonding. All right, so together the 2 are stable. So, covalent bond. A covalent bond is electrons are shared between 2 or more atoms, so they cooperate. Covalent bonds, they're shared. Polar covalent bonds. Now this is very similar to covalent bonding. The electrons are pulled unevenly toward one end of the molecule. This results in one positive end and one negative end. A great example of this is water. Okay, so let's go ahead and bond with the dots. We're going to use what's called the Lewis dot diagram model. All right, so if an element has 3 or fewer valence electrons, it will usually drop those electrons. Like, go ahead, take them. This ion then becomes positive, so there's less electrons. So if you think about if you've got positives and negatives, if you've got take away a lot of the negatives, you're left with nothing but positives. This is going to cause the overall ion to become positive. Now, the opposite of that is if the element has 5 or more valence electrons, we'll usually steal the electrons to get a full octet. And you guessed it, this will make the ion become negative because now you've got more negative electrons than positive protons. So if an element has 4 electrons, it will usually share to get a full outer level. This is called, again, a covalent bond. All right, so let's start talking Lewis dot diagrams here. So I'm going to talk about this, and I realize that this may be a little boron, but stick with me. So a boron's atomic number is 5. So step 1 is subtract the pair. You get 2. Remember first energy level. So 5 minus 2 is 3. So you have 3 electrons left over. Can you get to an 8? Nope. So you're done. Okay, so then you draw the dots. Let's try it with argon. And I was going to try to do some more puns about chemistry, but I think all the good ones are gone. So let's continue. All right, so again, you subtract the pair. You've got 18 minus 2, so there's 18 total electrons. You subtract 2 for the first energy level. That gives you 16 left over. Step 2, can you get to an 8 for the next energy level? And yes, you can. So you subtract the octet. 16 minus 8 is 8 electrons left over, and then you draw the dots. So in this one you've got 8 electrons available for bonding. This is kind of what it looks like, so let's try this again. All right, so again, we've got boron here, right? So you've got five electrons that are around that you need to deal with. So up in the upper left-hand corner, that is the number of electrons, or excuse me, it's the number of protons, which equals usually the number of electrons available as well. They're usually balanced. So here we go. So you've got five total electrons, right? And also you will see the electrons abbreviated as E with a negative. That is their charge. So lowercase e with a negative charge. All right, again, so we're rolling with the octet rule, which is 288, energy levels, 288. There's 2 in the first energy level, as you'll recall. So 5 energy total minus 2 in the first energy level is 3 electrons left that are available to deal with. So you've got 3 electrons on the next energy level. So now we're on the second energy level. Let's go ahead and see what this looks like visually. Okay, so there's our energy levels. There is our nucleus, and I realize there are way too many protons and neutrons in that nucleus, but let's just go ahead and play along for now. All right, so we are drawing them, and so with the Lewis dot diagram, we go ahead and draw it around the first energy level, and as we determined in our calculations, we have 2 electrons in the first energy level, so we go 1, 2. Then we go, okay, so I've got 5 total. I took away 2. That means I have 3. So the next energy level, we go out, and we have 3 available for bonding there. So we go 1, 2, 3. Now, when you draw them, make sure that you draw them. You can draw them anti-clockwise or clockwise, whichever, but make sure that you don't pair them first. Draw them around the circle. And if they pair up after that, great. All right, so let's move on to argon. So argon has 18 total electrons. Again, we're going to do the octet rule of 288. So you've got 18 total electrons, again, E negative for the charge. So there's 2 in the first energy level. Again, octet rule, 288. So you've got 18 total. You've got 2 in the first level, which means that there are 16 left. So 18 minus 2 is 16. So you've got the first level covered. You've got the second level covered. So you've got 16E minus 8E on the next energy level. So you've got 2 on the first, 8 on the second, and you've got 8 electrons left over that are available for bonding. This is like the perfect example of the octet rule, 288. So let's go ahead and see what we've got. So you've got 8 electrons minus 8 electrons on the next energy level, which means you have 0 electrons left, which means everybody's happy. All right, so let's go ahead and see what this looks like visually. All right, so there's our energy level. Again, way too many protons and neutrons in the nucleus, but let's roll with it. So we're going to go ahead and draw our electrons. Again, octet rule is 288, so we've got 2 available, so we go 1, 2. Then that's all set for the first energy level. On to the next energy level. In this energy level, we've got 1, 2, 3. Now we're going for a total of 8, right? So we've got 2 on the first level, and then 8, following the octet rule. So we've got to get 8 electrons around here. And remember what I said, you sort of draw them separately, but if they come together, that's cool. So there we go. So now we can start pairing up these electrons. And now I've got 8. 2, 4, 6, 8, all the way around the second energy level. So that means the second energy level is happy. So we can move on to the third. Let's see what we got. All right, so our third energy level. So it looks like we've got 2, 8, and we've got 8 left over. So let's see how that works. So we're going to go ahead and put 1, 2, 3, 4, 5. And again, they're starting to match up. 5, 6, 7, and 8. So let's go back and double check our math here. So we've got 2 in the first level, and then 8 on the next level, and then 8 on the next level. So we can actually reverse it. So we've got 2 plus 8 is 10, and then we've got another 8, which is 18. Does that match up to the total number of electrons of 18? Yes. And so if you'll look at this, argon is all balanced on the outer valence shell, which means that it has all of the electrons that it needs. So it really doesn't care all that much about bonding. It is a stable element, also known as a noble gas. So noble gases have no valence electrons that are available for bonding. So they're stable. So they do not have to bond to have a full outer layer, so they're good. They're just like, I'm good, man. I'm not really, I'm kind of stable. I really don't need you. I got what I need, whatever. The noble gases are on the far right of the periodic table, including helium, neon, argon, krypton, xenon, and radon. And that is about it. Hope you liked our lecture, and I will leave you with the Russian Orthodox Church. All right, it's been nice bonding with you. Bye.